Uh, Hello, everybody. Well, today we're gonna uh, welcome Professor Dohyun Kwon from Seoul University of Seoul, Korea. So let me introduce him a little bit. And he got his PhD at UCLA, June 2020, and then he uh, was then Black visiting assistant professor at uh, University of Wisconsin at Madison during August 2020 to February 2023. And then from this March, so he became an assistant professor at the University of Seoul, Republic of Korea. So I'm very happy to invite him here. And today he's going to talk about the level set first mean curvature flow with the Neumann boundary condition. Please welcome Professor Kwon. Please.
Yeah, thank you so much for this nice introduction. And then I really appreciate the invitation here. And also thanks all for the organizers. Today, I'm going to talk about the levels and first mean curvature with the Neumann boundary condition. And this is my recent work with Hong Tuan, who was my mentor at UW Medicine, and Ji-Young Jang and Hiro Mitake at University of Tokyo. Please feel free to interrupt me if you have any questions. So I will briefly talk about mean curvature flow first, and then I will discuss local Lipschitz under the Neumann boundary condition. And then I will explain our mean result on global Lipschitz, and then we will talk about large time behavior. So if you have time, then I will give some remarks on our assumption, which is the coercivity assumption. Okay, let's get started. Okay, so as you may know, mean curvature flow is a geometric flow of an evolving set, and then the boundary satisfies the following condition. And we will consider the first version of mean curvature flow here, and then C is called a forcing term, and kappa is the usual mean curvature. So typical and also classical and important case is the case with C is identically zero. And in that case, the flow can be understood as follows. So if the surface is maybe close to, or maybe let's say flat, then the kappa is close to zero. And if depending on the convexity, kappa can be negative and then positive. So as time goes, one can see that. Let me start the video. In this case, and also in two-dimensional space, it converges to a point and as follows. So let us wait a little bit more. All right, there you go. So our main equation is given as follows, and here we will consider the level set formulation of mean curvature flow. So I will talk about that more later, and let me define that first. So we are interested in gamma t, which is basically the boundary of the set I described earlier. And we are interested in the function u such that the zero level set of u is given by gamma t. Under this formulation, our normal vector is given by du over modulus of du. And mean curvature is equal to the divergence of the normal vector. So kappa here, the mean curvature is given by divergence of the one I mentioned. By using this formation, one can, first of all, rewrite the mean curvature flow equation as follows. So the left-hand side is normal velocity, given by UT over the modulus of du. And then, as I mentioned, divergence is, mean curvature is divergence of the one here plus our Worthington Cx. And as I mentioned, we are interested in the Neumann boundary condition. So the second line is the one there. And then the last one is the initial data. So here is our main equation. So let me summarize this equation a little bit once again. So basically, the normal velocity is given by mean curvature plus c, and Neumann boundary condition here is indeed, that means the boundary gamma t is perpendicular to the boundary of omega. So yeah, as described here. So let me give you maybe quick simulation here. So if our initial shape is like this cat, this is actually called wildcat. And then as time goes, it converges to, so depending on C, so if C is 0, then it also extinct. But in this case, I chose volume preserving C. So in that case, it converges to this shape. And then as you see, this satisfies the Neumann boundary condition. All right. And our main questions are as follows. So for this equation, normal velocity is equal to mean curvature plus c. We are interested in well-postness. And then we are interested in regularity, in particular Lipschitzness, and then we will discuss the lifetime behavior. So first of all, let us talk about the well-postness first. So as you may know, the operator here, so since we consider the level set formulation, so if you define f as follows, so trace of the identity matrix and then this tensor product times x, then one can easily see that our equation can be rewritten as follows. So the important part here is, unlike the usual Laplace operator, which is trace of x, our operator is not uniformly elliptic, but only degenerate elliptic. So that means that, unfortunately, higher regularity is not expected here. And then the well-postness and the comparison principle are discussed and also well established in the theory of discrete solutions. For instance, Chan Gigagoto, Evans Brock, et al. So then let's talk about Lipschitzness. Let's move on to the Lipschitzness. So in Giga Onumasato's paper, they discussed that if the domain is convex, here domain is omega, then C is identically 0. The classical mean curvature flow gives global Lipschitzness. But they also illustrate that if the domain is not convex, then C is identically 0 might not be good enough. So they proposed one example that as time goes, it converged to a characteristic function. So I will discuss about that in a moment. So let us start with very simple example first, and then I will also give you some more intuition about the levels of formulation here. So simplest case, C is identically 0, and then our domain is convex. So let's say that our domain is just like one single strip, and then U is given as follows. So on the top, U is 2, and then bottom, U is identically 0. And then we will just choose a linear interpolation of U between U equals 0 and then U equals 2. Then as time goes, you see that it satisfies all conditions we need. So for like each level set, kappa is 0, and then it also satisfies the right angle condition. So as time goes, it stays, and it is basically a stationary solution of the equation. Now let us slightly change the problem. So, and see what happens if we consider different domains. So still C equals identical to 0, and then convex domain. And then, yeah, this is like slight modification of the domain here. And as you can easily see that as time goes, because of the curvature term here, so like for instance, I think you can see the cursor here. So the level set of U equals 0.5 goes down to here. So that basically means that U increases on the like lower part of this domain. So that means as time goes, you convert this to 1. So again, U is Lipschitz as in Giga's result, and then yeah, it converges to U equals identically 1. All right. So then the interesting example also proposed by Giga Onumasato is given as follows. So previously, since the domain is convex, and then we can easily see that all like level set here has like some signs. So like for instance, we can easily see the direction of each level set, and then we can expect that it converges to the same value here, 1. But here, as you again see that it is indeed possible to make some kind of level set, like for instance, the blue one here, such that this level set may converge to like the one here. So what does that mean? That indicate that, so like here again, we may consider appropriate interpolation. We choose that as an initial data. And then as time goes, for instance, here, that moves down. So that means that you also increase. So like let me just say the conclusion here. So that means that it converges to the characteristic function. So we have a line here, and then like all point above this line converge to 1, and then like U equals 0 stays. So that means that you convert to a characteristic function, and of course this function is not Lipschitz. So that means we cannot guarantee the global Lipschitzness here. So we may or we may not have like local Lipschitzness, but unfortunately, that means that like in this case, if the domain is non-convex, then we cannot expect the global Lipschitzness. So I will come back to this example later, and then we prove that in the first like version of curvature flow, and we indeed prove that this like converge to the characteristic function as time goes by using subsolution and supersolution. All right, so our main question is as follows. So C is identical to 0 is not enough to ensure the global Lipschitzness. Then what is the optimal condition of C to make sure that U is globally Lipschitz? More precisely, we are interested in the following question. Find the relation between the first C and then the convexity of the domain. So I will discuss that like today. So let's talk about the local Lipschitzness first. So local Lipschitzness indeed can be directly follows from first time method. So here is the result. So here, U is the unique viscosity solution of our equation, mean curvature flow with Neumann boundary condition. And we assume that our forcing term is C1. Then we can find a constant M and then also like C sub t, and C sub t depends on time, such that this function is Lipschitz. And here, local Lipschitz means the time is between 0 and t. So the idea is as follows. So we may think the approximate problem. So here, approximate problem means we may consider the graph setting of mean curvature flow. So what is the difference between the graph setting and then the level set formulation? So I think like some of you are familiar with the case with epsilon equal 1. So in that case, this coincides with the graph mean curvature flow. And in that case, the operator here, I denote this by B, not exactly B, but the operator here is uniformly elliptic. So that means that we can say that our U is smooth. So that means that we can differentiate this. First of all, that's nice because like previously, we cannot even expect like Lipschitzness. But in this case, we can say that U epsilon is indeed the classical solution. So that means that we can differentiate this fairly. So let me introduce some notations here. So since we consider approximate problem as epsilon here, so that means that we can simplify the notation as follows. So UT minus some like mean curvature term, and then the forcing term here. So here, we will use the Einstein summation notation. So I will use this to give some brief sketch of this. So my laptop is not charging right now, so please give me a second, sorry. Sorry about that. Okay, sorry about that. Okay, so back to the uniform bound. So from the previous like observation, we will basically differentiate the approximate problem and then using this to prove the following lemma. So this lemma says that the initial data, so UT epsilon, the uniform bound of UT epsilon is bounded by the bound of UT epsilon at time 0. So the idea here is I mentioned differentiate the previous equation. So we do have like more term here, but you can actually see that this is indeed the important part is the first two term, the red part. So let me maybe show you once again here. So the original equation, we have UT minus mean curvature term minus the forcing term. And then in the second one, the differentiate one, we do have more term here, but as you see, all other terms except maybe the first two terms, we have UT and then I and then UT sub J and then UT sub L. So we will use maximum principle. maybe as expected. So then all other terms vanishes. So we can prove that our desired result here. So like we can choose the maximum point and then differentiate this, and then we can conclude that maximum should obtains at time zero. So this is the basic idea of the local Lipschitzness, and then this is standard result. But let me introduce this because we will also use this in our main result of global Lipschitzness. So this is how one can prove the lemma. All right, so global Lipschitzness. So here, we need some assumption here. So we will call this as the coercivity assumption. So let me explain the assumption in a moment, but let me introduce our result first. So the only difference here is we have constant M and L, and now it does not depend on time. So for all x, y in omega and then also ts, so any positive numbers, we have the following result. Then our assumption C here depends on, first of all, the eigenvalue of the like d normal, and then also the diameter of interior ball. So I will explain this assumption now. So first of all, this left-hand side indeed appears in the homogenization of degenerate publication. So this indeed naturally comes from the Bernstein method. The Bernstein method, I meant differential indication and then define the condition that the solution is global Lipschitz. Then you will get this left-hand side. And what about the other term? So left-hand side should be greater than 0, and also it should be also greater than the one here. So C naught modulus of Cx plus 2n C naught over K naught. So here, the simplest case is, again, the case that the domain omega is convex. So in this case, the eigenvalue of dn, so that is always positive. So that means that minus lambda, which is always negative, so that means that C naught is always less than or equal to 0. And we will consider the diameter of interior ball. So that means that in that case, you can check that the right-hand side is 0. So this like coincide with indeed the Ki-Ahm result. So in that case, indeed, C is identically 0. So sorry, we do have like many C's. So Cx is identical to 0 is indeed enough to satisfy this condition if we don't have like delta here. So we needed to have delta because we would like to consider like unbounded domain. So that's why we do have delta here. But indeed, in a bounded domain, we may not need delta. All right. So this is like very first remark on the assumption. And then if you have time, then I will explain more about this condition in the last section. All right. So as in the second part, local Lipschitzness, we will do exactly same job. So consider the linearized equation. So we would like to find the equation of W. W is square root of epsilon square plus modulus of du epsilon square, and then apply the maximum principle. And then fix a point, and then here we do have two cases. the interior case and then the boundary case. So case 1 is indeed very similar to what we did earlier, and then case 2, the boundary case, can be interesting and also like important. All right, so the interior case, after going through all steps, this is exactly what we obtained. So we do have the equation here. So the first equation, the modulus of dw squared is greater than or equal to this. And since we would like to have contradiction, so that means that if you compare the term, the coefficient of the higher order term here, w squared, then we can show that ut is indeed bounded. We can reach the contradiction. And that's why, indeed, why we do have the equation here. So this left-hand side is appeared in the coercivity assumption, so 1 over n cx squared minus the modulus of cx. And this is exactly why I told you that this assumption naturally appears from the Bernstein method. So compare this and then also cx naught square. And since we assume that this like 1 over n cx squared minus modulus of dc is greater than delta. So that means that the coefficient of w squared on the right-hand side is greater than the 1 on the left-hand side. So we can prove that w is indeed bounded. And what about the boundary case here? So first of all, we can maybe think about just what happens if we just differentiate this with respect to normal. So consider the directional derivative of w and then see whether we can apply the maximum principle as we did. So then you can see that like by using this like simple calculation, you will see that we obtain the following. So here C naught is again the eigenvalue of dn. And you see that as in remark here, if the domain is convex, then C naught is less than or equal to 0. Then by just directly using this equation, this directional derivative is less than 0. And this indeed gives our desired result, because that means that one cannot attain the maximum on the boundary. So yeah, we are done here. However, unfortunately, if the domain is not convex, then C is not necessarily less than or equal to 0. So that means that the right-hand side, like C naught W, can be positive. So then how to like solve this issue? So let me explain the idea first. So why don't we consider some kind of multiplier here? So instead of choosing just W, W is basically the modulus of du. If we have this kind of function, then it would be nice. So this function satisfies some condition, and then if you can say that this function, the directional derivative of this function is less than 0, then we are done. So we would like to find a function that satisfies the condition here. So first of all, at the maximum point, this function is 1. And then we want this is less than or equal to 1 to have the inequality, and then also to have the last equality, right-hand side is 0, we want to have the equation here. Then, if you can, let's say that, let's accept that we can find this function, then the argument is exactly given as before. So using this function, then we can apply the maximum principle again, and then at the minimizer, we can find the equation. Then the argument is indeed like parallel to what we did. So left-hand side is, you see that this is exactly the same as what we did, except instead of the x0 t0, we consider x1 t1. And right-hand side is the one depends on c0, which depends on the convexity, and then k, which is the diameter of the interior ball, and then we do have w square. Then, as you may expect, it is enough to compare the coefficient of higher order terms, and then if that one has the correct relation, then we can conclude that W is indeed bounded. So that's why we do have the condition I described previously. So that's why we do have the right-hand side depends on C0 and then also K0. So you can check that this condition is exactly comes from our calculation. So this is our main result, and then I will discuss the lifetime behavior first based on this result, and then I will talk about this optimality of this condition more later. All right. So since we do have the global linearness, then that enables us to prove the lifetime behavior as follows. So that means that we can find Lipschitz function V, and then one can also verify that this function is the stationary solution of our equation. And the proof is by using the Lyapunov function, and then because this equation is kind of understood as the gradient flow mean curvature, gradient flow of the parameter functional. So one can use this to conclude that our solution converges to stationary solution. So this is the brief idea. And then since we here again, it is easier to like work with the approximate problem. Otherwise, it is not easy to differentiate that. So that's why we consider approximate problem first. And then one can prove that this L2 norm of UT is uniformly bounded. So that's how one can prove that. And then the rest of idea is, since we do have global Lipschitz, so use Arden-Laskoli, and then one can find some function. Then the last argument would be, since this is stationary, so we are done. So this is like a consequence of our global Lipschitz. All right, so then let's move on to, so we do have 10 more minutes, right? Yeah. So let me talk about, the last one. Okay. So as you see, this condition comes from our like derivation, like all global Lipschitz and then also local Lipschitz. Then one natural question here is this condition optimal? So this, first of all, there are indeed, I would say, like some studies about the left-hand side is greater than 0, for instance, Capari-Bono. And what about the other one? The one depends on the domain, so eigenvalue and then diameter. So we like to somehow understand this more, and then we are actually able to find explicitly. So this is indeed like simple, but this helps us to understand the condition here. So let us consider the following domain. So the region is, the interior is between these two parabolas. And in this case, one can explicitly compute basically everything. So the diameter of interior ball, and then also curvature here. And if it does not satisfy the condition, then indeed one can find the following stationary solution. So in other words, depending on the diameter of the interior ball, so this one is like basically the one here, and then the curvature depends on depends basically let me just say that M and then the K, so that is like that gives the all condition here. So depends on M and K, one can find stable stationary solution, or it may like only have unstable stationary solution. And this is the stable one. So if we have stable stationary solution, then means that as time goes, it converts to that stable stationary solution. And since that solution is a characteristic function, so that means that that function is not globally diffused. So that means if our condition is not satisfied, then one can like conclude that global diffusion is not necessarily true. So this example gives, I would say, like some idea here. Although in this example, we just consider constancy. So in this case, one can explicitly compute the standard solution, but otherwise, it is not easy to like construct this solution. So this is basically one just find like so this is a part of a circle, and then if the forcing term is identically zero, then one can find the stationary solution. So it actually have like more stationary solutions. So it has like two more unstable stationary solutions. And it is actually interesting for us that depending on the geometry of the domain, we may or may not have stable solution. All right. So one interesting problem. So I think that there are like many experts here in audience, and you see that the example I described is somehow can be understood as part of this perforated domain. So like, for instance, if you just consider like this part here, so this is basically the square minus a ball, and the white part is the interior of the domain. Then question here is, under the condition we described, does the homogenization of this first mean curvature occur in a periodic setting? And homogenization here means like instead of the original equation, we do have like epsilon parameter here, and then as epsilon goes to zero, what happens? And it turns out that maybe like audience like can answer this question, or I will be happy to talk about this. And it turns out that although we do have global richness, this is not that simple. So I discussed the Caprari-Mono's result. So in that case, like the domain is the Euclidean domain. And then they discussed that like the condition I described is like, so the result is indeed like divided into some part, but let me just summarize that. Because of the degeneracy of this operator, although we do have global richness, proving homogenization is not that simple. So if you have any ideas about that, then I would be happy to talk about that. All right, so that's all, and thank you for your attention.
Thank you, Professor Kwon. Any questions? So you can raise your hand or you can type on the chat board or, whatever method you prefer. Okay, since there is no question yet, so I will ask one question. So you
Sure.
talk about the conditions, on the curvature and the forcing terms to drive the ellipsogenous. So then maybe it looks like, was it like a small perturbation of C is necessary to guarantee it? Like, well, it is a very complex conditions.
Yeah, it is.
And also there is a delta terms which occurs
Yeah.
the conditions. So then could you tell us when your condition is satisfied and when is not satisfied? Then it will be more clear.
Yeah, so yeah, that's a good point. So first of all, delta one. So in a bounded domain, we don't need delta. So that's
Okay,
actually what
sure.
I described here. And then the other term, so like say not blah blah blah. So first of all, the convex one, as I mentioned, the right-hand side is just zero because we take the maximum between 0 and a negative number. So that's the second like simplistic example. Like simplistic example. And then the second simplest one is indeed the one I described here. So basically this K, so 2K is too small K is basically the K naught I described here. So
Okay.
this is the minimum of the interior ball. So in this case, as you see, the minimum one is like that. Yep. And then M is related to like C naught here. So like one way to describe this is I think as follows. So we would like to have like this kind of solution. So this is what we just construct explicitly. But for instance, if we decrease K, so we can just like translate like the parabola like that. So that means that we do have bigger right-hand side. So I think I should show you. Yeah. Decrease K and then bigger right-hand side, then this may not be satisfied. So this is like one way to understand that.
Somehow, like, well, if you right-hand side is bigger, then well, you at first you expected gradient of C should be smaller.
Yeah.
Yeah. So in the
Right.
your first term is almost flat. Something
Yeah.
like
Right.
I can see the balance between them. Okay.
Yeah.
I see.
Yeah.
So, any other questions? Okay, please.
So, Dohyun, thanks for this very interesting talk. I found that the talk is actually somehow related to an optimal regularity result of the PDE. Of course, you have to take into account the condition of the domain as well.
Mm-hmm.
But I was wondering, okay, so Lipschitz condition is like, okay, you are at L infinity. Do you
Mm-hmm.
think there might be a condition on the domain and on C as well, where you would rather obtain as an optimal condition that the time derivative is in LP?
Okay.
So it is integrable,
yeah.
Q integrable, for instance, you know, and instead of getting that it is Lipschitz. And then in T, it would be basically a weak derivative in the sense, you know.
Yeah, I understand. So I think this is very interesting question, and then I'm also curious. So one thing I'm actually thinking of is like what about if we use some kind of variational structure instead of Lipschitz? So for instance, not exactly LP, but can we have like BB bound? So like if we use like the gradient flow structure of mean curvature, then we may expect BB bound. So BB bound is like weaker than the least condition here. Then, but still we can somehow find the limit. So I think that I hope that I don't know I cannot actually say, but I think in that way we can maybe relax the condition. Yeah. But I'm not exactly sure about LP. Yeah.
Okay, so I can give one remark.
Yeah.
So well, like in the usually PD problem, so if you perturb, well, let's say you expect the use of T is LP, that means it's like a W2P estimate. Okay, so then well, with some constant coefficient, you have a very nice regularity. But if you have like a more continuous data, then or continuous coefficient at diffusion term, then you may expect a W2P.
Yeah.
Okay, so then if you fix the coefficient with a constant, but let's say you perturb your boundary a little bit, okay, then you can make a change of coordinate so that your perturbed boundary is nice, but that perturbation goes to the PD after change of variables. So if you balance them, then maybe certain change perturbation of boundary goes to the perturbation of coefficient, and then you get the W2P. So that's the one of the way to create some a little bit irregular boundary to get the W2P. Well, that is just intuition.
Yeah. Interesting. Thank you.
Yeah, and the thing is that this is a Lavoisier method. So time derivative implies the time derivative of the boundary level set times the gradient. So even though the gradient term is uniformly bounded, but the time derivative of the level set may be W2P, because that is the zone of the usually standard mean curvature equation for the graph works. So there is a linkage. Yeah, so maybe you can create a certain example to get the W2P, which is optimal. Yeah, so yeah, that's my guess. Okay.
And then since it is a little bit irregular, the domain is not convex anymore. So
it could be, yeah, irregular. A little bit, maybe it's a convex, but even though it is a convex, maybe, still there is oscillation there.
yeah, asymptotically it's convex, but it's not.
Yeah, convexity is not C2,
Yeah.
is C11. So there is a certain room of perturbation still. Yeah.
Yeah, it's good. Thanks.
Yeah, it's an interesting question.
Yeah, thanks for the question and comment. Yeah.
Okay. Another questions? Okay. Otherwise, we're gonna let's give the thanks to speaker again. Thank you. And we are going to have a coffee break in 5 or 10 minutes. So maybe Daniel will send will link to everybody. So please join
Actually,
us.
you received all the link already.
Oh, okay. Very good.
Yeah, so in the reminder email to today's seminar sent by Zoom, you have at the very bottom, there is actually in the reminder email is a link to the coffee break.
Oh, so you send them together.
Yes, exactly.
Oh, that's very good. Nice. Okay. See you guys soon. Bye.
Okay.
Okay,
Thank you. Thank you, everybody.
Bye.